Today's lesson, section 14.1, we're talking about combinatorics. Now here, this is just like an added section to our chapter 12 discussion of sequences and series. So it's not like in the same area of expertise, but it's related to it because we're talking about numbers and kind of looking at patterns and discerning those. It's just a little easier for these patterns because we're not looking at the same stuff. Okay, so there's three things we want to talk about: the fundamental counting principle, permutations, and combinations. So fundamental counting principle says that if you have two events that occur in order, and if the first event can occur in m ways and the second event can occur in n ways, so the first occurs already before the second, then the two events can occur in m times n ways. Now, this is not restricted to just two events. You could have multiple events, but they just all need to be separate from one another. So they can't be the same event happening twice. Okay? So, for example 1, a restaurant offers 5 kinds of beverages, 6 kinds of main courses, and 3 kinds of desserts. How many possible meals can one person get at this restaurant? So here you have one distinct thing, which is the beverages, another distinct thing, which is the main courses, and another distinct thing, which is the desserts. So they're all separate from one another, so you can just multiply them. So 5 times 6 times 3 would be the proper way of finding this value. So 5 times 6 times 3 gets me 90. So there's 90 meals that I could create while being at this restaurant. Okay. The next thing is a permutation. Now, a permutation just on its own is a set of distinct objects and is in an ordering of these objects. Okay. So I have 3 shapes here: a triangle, a square, and a circle. And so I want to be able to order them into different orderings to see how many ways I can order them. Okay, so that would be a permutation. So using them all is the key thing. So triangle, square, circle, triangle, circle, square. Do a better square. And then circle, square, triangle, circle, triangle, square. And then square, circle, triangle, square, triangle, circle. So there I have all my 6 ways of ordering these. Okay, I put each one first and then switch the other two's order around for each one. Okay, now another way of finding permutations is if you just have n objects, you're not doing, like, you're using them all. Okay, then it's the same thing as doing n factorial. So n factorial, it means that you do a number. So like in this case, I have 3 distinct objects. Okay, so then my factorial would be 3 factorial. And when I want to find factorials, it's the same thing as you start with this first number, so 3, and then you just multiply to each number as you move down to 1. So 3 times 2 times 1. So in this case, I get 6, just like I got up here. Okay, now I could also do this for like 7 factorial, so it's 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, and then that would get you 5040. So that's kind of what a factorial is. It's always the highest value and then all the consecutive values after that to 1 all multiplied. Okay. Now, you can also do something else with permutations where you have n objects, but you don't use them all. So you're selecting a few of them at a time. So that would give us this formula. So permutations of n comma r is going to be equal to n factorial divided by n minus r factorial. Okay? So here I have a group of 8 people in example 2, and they're lined up for a concert. The first problem wants us to find how many ways are there to line them up. Then the second part is there turns out to be only 3 seats, one in the front, one in the middle, and one in the back. The rest of the people in the line are turned away. how many ways are there to seat the people? So the first one, since you're using all 8 people, and order does matter because Sally before Terry is different than Terry before Sally in this case. So I would say 8 factorial. So 8 factorial will be 40,320. Okay. Then letter B is a little different because here you're only selecting 3 of the people out of the 8. So not everybody gets to be a part of the concert apparently. So then we say 8 comma 3. So 8 is our N, 3 is our R, and we plug it into our formula. So then 8 minus 3 factorial on the bottom, and with 8 factorial on the top. Now here, if you want to plug this into your calculator, the factorial button, if you press the math button and go all the way over to the probability one, it says PRB. The 4th one is a exclamation point, it represents factorial. So you can use that if you want. Also in that same area, you have permutations and combinations that you can use with like our formulas that I'm going to give you. Okay. So any of those you can use. I just like to choose to write out all my work because that's just who I am. So 8 factorial, and then 8 minus 3 would give me 5 factorial. Now, how I would reduce this is that I work the factorial on the top so that I get a factorial that matches the bottom one, or the highest bottom one. So 8 times 7 times 6 times 5 factorial. Because if you take any, like the top number out, so like if you took 8 out, it would be 7 factorial. If you took 7 out, it would be 6 factorial. You could do that with any of them. So you're not getting rid of them, you're just rewriting them so that you can reduce a lot of stuff away so you have less to work with. So now 8 times 7 times 6 gives you 336 ways to order those 3 people. Okay. Now the next thing is combinations, very similar. The formula is very similar as well, but now you just have a R factorial in the denominator. So permutations cares about order, combinations does not care about the order. So that's why the R factorial is added in there, because it's going to take all of those other combinations, or like things that kind of match up, so you're using the same 3. So if you go back to this example, since you're using all 3 of the same, like a triangle, square, and circle, for combinations, because it doesn't care about the order, triangle, square, circle is the same thing as square, triangle, circle. And so all of those permutations or ways reduce down to 1 way because you're just using all 3. So you get a completely different answer depending on which one you use. So combinations will always be less because you're taking out all of the extra ones, the ones that overlap kind of, because the order doesn't matter. So example 3 here, it says a student must answer 7 of the 10 questions on the exam. In how many ways can she choose the 7 questions? So here, because you have 10 questions, it doesn't matter if you pick the first one, the second one, like in that order, or if you go to like do 2 first and then you do 1 and then you do 4, that thing. So it doesn't matter which ones you pick, just as long as you're picking 7, right? So here we put 10 is my N, 7 is my R. So then 10 factorial divided by 7 factorial times 10 minus 7 factorial. So that gets me 10 factorial over 7 factorial times 3 factorial. Okay? So now here, a couple of things just to make sure that you're doing it right. In your denominator, the 2 factorial numbers should add up to the factorial number at the top. So 7 plus 3 equals 10. So it needs to be that way. And so if you have multiple, sometimes with some of the trickier ones that you might come across, you may have like several things in the denominator, but they all should add up to the thing at the top. So just a helpful hint there. Now I want to do the same thing I did with the permutations with my 10. So I reduce it down to the highest factorial. So 10 times 9 times 8 times 7 factorial. Those cancel out. Also, with the other factorial at the denominator, I like to multiply it out so I can see if I can reduce anything with the top. So the 3 goes into the 9, and the 2 goes into the 8. So then now, all you have left in the numerator is 10 times 3 times 4, which is 120. And then the denominator is just 1, so it doesn't matter. So here, I have 120 ways to answer 7 questions on this exam. Now some tips that I'd like to tell you is for each method. So for fundamental counting principle, this is for problems that are making consecutive or different choices. Okay, so they're like pick 4 out of hat, pick 3 letters, and choose 2 of the beverages over there. So they're all different things, but you just can multiply them distinctly to each other to get the number of ways to do it. Permutation, like I was saying, order does matter. That's what makes it different. Combinations doesn't matter. I gave you 2 more examples here. Permutations example here is 8 people to select from, and you are trying to fill a spot for the president, vice president, and treasurer. So you have 3 spots, but 8 people to choose from. So, and it matters. So Sally being the president and Terry being the vice president is different than Terry being the president and Sally being the vice president. Okay? So those 2 things are different, so that's why order matters with that one. Combination example would be if I have 8 people to select from and you have 3 spots to fill to go on a trip to Colorado. So if I pick Sally first, Terry second, and then Jim third, it doesn't matter if Jim got picked first instead, and then Sally, and then Terry, because that's the same. You're still taking the same 3 people. Someone's feelings still might be hurt because they weren't picked first, but that's not really our problem. Okay, so have fun.